Okay, let's dive right into this explainer. Today we're going to take the incredibly complex, honestly sometimes highly abstract architecture of enterprise NestJS, and we're going to map it to something we all fundamentally understand. We're talking about a highly secure, well-oiled, massive hospital. We're calling it the Citadel. Listen, if you've ever felt completely lost in a sea of dependency injection, middleware, guards, pipes, interceptors, and repositories, well, this is absolutely for you. We're going to follow a single patient's journey, step by step, from the exact moment they walk up to the building, all the way to the moment their medical records are securely stored in the basement vault.
Think about it for a second. By visualizing your code as physical spaces, from the architectural blueprints to the front gates, all the way down to that basement vault, we can completely demystify how these advanced enterprise systems actually operate. Seriously, you're never going to look at a NestJS module the same way again. We aren't just looking at code today. We are literally walking through a physical district. In fact, you can think of your NX monorepo as the city's zoning laws. It's the structural boundary ensuring the public web portal and the private hospital backend never ever illegally cross boundaries.
So here is our architectural floor plan for today's tour. We'll start with blueprinting the Citadel, then securing the front gates, navigating the customs hall, moving down to the specialists and the vault, and finally, scaling the franchise operation.
Let's kick things off with Section 1, Blueprinting the Hospital Citadel. Laying the foundation.
Before we can even think about opening the doors to our very first patient, we have to actually build the hospital, right? We need to define exactly what wings exist and, of course, hire our staff. Every great building starts with a plan. In NestJS, your main TS file is essentially your ribbon-cutting ceremony. It's that grand moment. The mayor cuts the tape and says, "This building exists," and the doors are officially open on port 3000. But the building itself, that is defined by the app module. The app module is your master architectural blueprint. It's a flat list that dictates exactly which hospital wings or modules get built by the factory. You might have a patient module, an appointment module, or maybe a billing module. Now here is the absolute golden rule of the blueprint. If a department or module isn't listed on that app module blueprint, it simply does not get built. It doesn't matter how perfectly the code is written in your files. If it's not on the blueprint, that wing doesn't exist in the hospital at runtime. Oh, and right before those doors open, the hospital checks its policy handbook, the config module, to ensure every single necessary environment variable, like your database URL, is strictly validated. No policy, no opening.
So the hospital wings are built. Next up, we need to staff them. Inside the NestJS Citadel, every professional wears a badge, which is a decorator, specifically the @injectable badge. When you stamp a class with this badge, you're officially registering them with the central staffing office. And this brings us to the absolute magic of dependency injection. Instead of a doctor having to walk all the way down the hall to the supply room to grab a patient file, dependency injection means the central staffing office just hands it to them right at their door. It gets dropped directly into their constructor. You literally never use the new keyword to instantiate a service inside another service. You just declare what you need, and the staffing office delivers it on demand. Most of these staff members are permanent singletons, staying on duty 24/7, but some, as we'll see a little later, are daily temps hired fresh for each specific patient visit.
Moving right along to Section 2, Securing the Front Gates. Let's look at our perimeter defenses.
Okay, so the hospital is fully built, it's carefully zoned by our NX monorepo laws, the staff are all in place, and the front doors are officially open. Let's see what happens when a patient walks up to the front gates. As they approach, they walk through the outer corridors. This space right here is your middleware. Think of middleware as the hallway CCTV cameras. It acts before you ever see a security guard, before you hit any intake desk. It records correlation IDs, it logs the incoming path, and it watches the raw request and response objects passing through. But here's the critical limitation you have to remember. Middleware is just observing and stamping. That's it. It decides absolutely nothing. It cannot stop a request based on your complex business logic. It's literally just a camera on the wall. Perfect for infrastructure tracking, but definitely not for deep security enforcement.
After passing the cameras, our patient reaches the actual outer wall. This is where they meet the bouncers. We call this the guard stack. To get past, our patient has to present their passport, which in our world is a JWT located right in their authorization header. Now these guards execute strictly in sequence, moving systematically from left to right. First up, the auth JWT guard does a cryptographic check to ensure the passport is actually valid. Second, the tenant guard checks if this user even belongs to this specific hospital rather than some different hospital in our franchise. Third, the roles guard looks at their department access card. Does their role actually permit them to book an appointment today? If any single one of these gates closes during this left or right check, Boom! The request stops dead in its tracks. You immediately get a 401 unauthorized. The patient is turned away at the door before they consume a single thread of processing power inside the hospital.
And this bouncer system actually brilliantly illustrates why we use different types of JWTs for different visitors. Our external patients, they carry RS-256 passports. Think of this as a public padlock. The central auth server signs it with a highly guarded private key, but absolutely anyone, including our gate guards, can verify it using a freely distributed public key. Because of this setup, even if our backend hospital gets completely compromised by an attacker, the absolute worst they can do is verify tokens. They can never forge new ones. On the flip side, our internal automated services, like background workers, they use HS-256 tokens. That's more like an internal office key with a single shared secret. It's much simpler, much faster, but it's really only safe for internal service-to-service traffic that never ever leaves the private network. And of course, Passport.js is our authentication specialist here, capable of reading both of these badge types completely effortlessly.
Now enter Section 3, Navigating the Customs Hall. Let's talk about intake and routing.
So our patient has made it past the bouncers with a mathematically verified passport. A slick little machine called the @current-user decorator scans their name tag so the system knows exactly who they are. But before they can go back and see a doctor, they must enter the customs hall. Here, the patient is handed an intake form. In code terms, this is your data transfer object, or DTO. The global validation pipe acts as the ultimate, totally unforgiving customs desk. It runs 3 rigorous checks on every single intake form that comes across it. First, transform coerces data types, so if a date is written poorly as a string, it transforms it into a proper date object. Second, whitelist silently strips away any sneaky, unexpected fields that weren't officially declared on the DTO. And third, forbid non-whitelisted is your enforcer. If any illegal fields are present, it throws a 400 bad request and literally shreds the form entirely. Oh, and right as they step up to this desk, there's an invisible observer, an interceptor, that clicks a stopwatch, recording exactly how long this entire hospital visit takes.
Once past customs with a perfectly sanitized intake form, the patient walks up to the reception desk. Now, depending on how they entered the building, they'll meet one of 2 receptionists. If they are a REST patient, they meet the controller handling gets and posts. If they are a GraphQL patient, they meet the resolver handling queries and mutations. Here is the absolutely crucial takeaway from this. The receptionist has exactly one job. Their only purpose is to translate the external HTTP or GraphQL request into an internal command. This means absolutely zero business logic happens at this desk. If you ever look at your code and see a receptionist prescribing medicine, like say checking if a user is over 18 inside a controller, that is a severe architectural failure. Don't do it.
Instead of trying to do the work themselves, the receptionist drops the sanitized file into the dispatch matrix. This is your CQRS layer, Command Query Responsibility Segregation. It splits all hospital traffic into 2 distinct lanes. We have the command bus, which is the change desk for things like booking appointments or updating records. And then we have the query bus, which is essentially a reading room for simply viewing medical history. Now, why do we separate reads from writes? Because simply reading a history file is incredibly fast and cheap, while booking a complex surgery is slow and highly transactional. By separating these intents at the architectural level, the hospital can easily build 50 reading rooms but maintain only 5 operating theaters, optimizing our resources perfectly.
Let's dive deeper into Section 4, Specialists and the Vault, Execution and Storage.
The dispatch matrix takes that routed request and sends it deep inside the hospital, straight to the brain of the operation. We are finally leaving the public intake area and entering the execution and storage levels. The command lands directly on the desk of the service layer, who is our specialist doctor. Notice how isolated this doctor is. The specialist doctor knows absolutely nothing about HTTP headers, JSON payloads, or GraphQL schemas. They don't care. They only know pure business logic. They basically just ask 2 questions. Is this medical procedure allowed, and what patient data do I need to make it happen? Because they are completely isolated from all those front-end transport concerns, the service doctor is incredibly easy to test in isolation. You don't even need to spin up a web server to test them. You literally just hand them a mock file and see exactly how they prescribe treatment.
When the doctor finally decides on a treatment plan, they don't walk down to the basement themselves. They delegate all database access to the repository, our Vault archivist. The archivist uses entities, which are official TypeScript record templates that map perfectly to your PostgreSQL columns, automatically translated into snake_case by our naming strategy.
The archivist also ensures that any major update, like booking that complex surgery, is wrapped in an ACID transaction, meaning if the power cuts out mid-write, the whole thing completely rolls back. It is a strict all-or-nothing database update. And crucially, you never ever alter this vault's floor plan with a reckless synchronized true command in production. That is literally like hiring an unsupervised contractor who might accidentally bulldoze a load-bearing wall. Instead, you use migrations, which act like controlled, completely reversible Git commits for your database schema.
Finally, we reach Section 5, Scaling the Franchise Operation, Handling the Load.
At this point, the Citadel is fully operational, perfectly handling our single patient. But hospitals don't serve just one patient at a time, do they? What happens when 500 patients arrive simultaneously at the exact same moment, all asking for complex records involving multiple doctors? To prevent a total system collapse, the hospital relies on the scale floor. First up, we have the DataLoader. This is our batch courier. If 500 patients ask for doctor profiles, a naive system fires 501 individual database queries. That's the dreaded N+1 problem. The DataLoader collects all 500 requests, bundles them into a single efficient query, and fans the results back out. But listen carefully. The DataLoader must be strictly request scoped. If it were a globally shared singleton, it might accidentally hand one patient's cached medical data to a completely different patient. Next, we have the bulk queue, which acts as the overnight mail desk. Heavy, slow work like generating PDF bills or sending confirmation emails is deferred here so the patient isn't just standing around waiting. Finally, Redis PubSub acts as the hospital PA system, broadcasting real-time GraphQL subscriptions, like instantly alerting a doctor's dashboard the very second a surgery is booked.
As the Citadel inevitably grows into a massive multi-hospital franchise, we face our absolute biggest security challenge, multi-tenancy. We have one massive shared backend, but Hospital A's patients must never, ever see Hospital B's records. A leak here is catastrophic. We solve this with defense in depth. Every patient gets a tenant ID stamped right on their entities. Think of it like a highly secure wristband. When they enter the system, a request-scoped tenant context reads that wristband. Then, an automatic fence called @authorize is silently applied to every single database query, hard-coding a strict filter for that exact wristband ID. By stamping the wristband, reading it on a per-request basis, and automatically fencing the queries behind the scenes, we create a foolproof defense that prevents cross-hospital data leaks even if someone maliciously tampers with a GraphQL query.
So let's bring it all together. Consider this your ultimate cheat sheet. It connects our physical hospital characters directly back to the technical code elements you're going to see in your NestJS repo. When you're staring at a validation pipe and wondering what on earth it does, just remember the customs desk shredding bad forms. When you're writing a resolver, remind yourself you are just the receptionist routing traffic. This character mapping right here is the key to mastering enterprise backend patterns without getting lost in the weeds of technical jargon.
And this brings us to the absolute golden rule of the Citadel. I want you to remember this. Arrows only ever point downward. Look at the architecture. Main.ts calls the module. The module loads the resolver. The resolver calls the bus. The bus calls the service. And the service calls the repository. No layer ever, under any circumstances, calls up to the layer above it. The archivist does not ask the receptionist a question. The doctor does not walk out front to talk to the gate guards. Information flows in one strict downward direction.
Understanding that strictly downward flow is the difference between an unmaintainable, tangled mess and a pristine, enterprise-grade application. The very next time you find yourself stuck on a bug or your architecture starts feeling a little fragile, stop and ask yourself, which layer of your Citadel just broke the law of gravity and tried to call upwards? Keep your layers strictly separated, keep your arrows pointing down, keep your hospital secure, and I'll see you in the next explainer.